Today we're going to be working on the pH scale, and the pH scale has to do with the concentration of hydrogen ions in the solution. Make sure that you get out a calculator because we are going to be working with not just regular four-function calculations, but this is actually a logarithmic scale, so you need a calculator that has a log button on it. We're also going to go into the pOH scale, which is very similar to the pH scale, except it's a measurement of the hydroxide ions in solution. So let's go ahead and take a look. Here we have the pH scale, and if you look over on this arrow, we have the pH, but we also have the related hydrogen ions here on the left side. So if we are looking at those hydrogen ions here, the bottom is 1 molar HCl, right? But as we go up, here's 0.01 molar HCl is here. Or this would be 0.00001 molar HCl here. So if you take a look at this, the 4 actually stands for how many zeros are between the decimal and the 1 in the molarity. So the higher we get, the lower the concentration of hydrogen ions is, which is why it becomes less and less acidic, right? This is the most acidic, and up here is the least acidic. In fact, this acidity is so low at a pH of 14 that the hydrogen ion concentration is 10 to the negative 14, which means we'd have to have 14 zeros. So if I say that pH equals 14, then that's the concentration of hydrogen ions equals, let's see if I can even fit 14 zeros. All right, so the concentration of hydrogen is so very low at a pH of 14 that it actually has no ability to interact, and the concentration of hydroxide is high enough to have the interactions when we get below 7. And so pH of 14, we have 14 zeros before that 1, so we have a very low molarity. So when we look at the power of hydrogen, or pH of some common substances, when we get down here at 0 and we go all the way up to 14, what you start to see is things like vinegar with a pH of 2.8, soda 2.9, orange 3.8 is actually fairly acidic. Your blood is at 7.4, and we have buffers actually to keep our acidity from changing up or down, because if we added a little acid to our blood through the carbon dioxide that we were breathing out, we could easily get down into the 4 range here, and that is quite deadly for our cells. And so we keep our blood at a very steady 7.4. When we get up here, we have ammonia, oven cleaner. These are heavy-duty bases. You should be familiar with the fact that an acid has a pH of less than 7, and what that means is the hydrogen ion concentration is greater than the hydroxide ion concentration. So that means there's more hydrogens than hydroxides. All right, and over here we have the opposite. We have a base, so we have more hydroxide than hydrogen ions, and that's what makes it basic. So here's that same concept that's on a new slide here, and remember that we can talk about a hydrogen ion as H3O plus or H or a proton, right, when we talk about these things in our equations. And so here our hydronium ion concentration is higher than our hydroxide, so that makes it acidic. Here our hydronium ion concentration is much smaller than our hydroxide, which makes it basic. In order to make a neutral solution, what we find is that our hydronium ion concentration equals our hydroxide ion concentration. So because they're equal, they neutralize each other, and between them they make water. Here on the left, the pH equals 3, and the reason the pH equals 3 is because we have 10 to the minus 3. In the middle, pH equals 7, and the reason is because we have a pH of 10 to the minus 7. And here pH equals 11 because the hydronium ion concentration is very low. It's down at 10 to the minus 11. So if we take a closer look, what this actually means is that each pH unit is 10 times as large as the previous one. If I change the pH from 3 to 4, that's only a times 10 change. But if I go from 3 to 5, it's times 10 and then another times 10, right? Which makes a times 100 when we change 2 pH units. It's 100 times more, but basic or acidic. Water actually can self-ionize. It can create a small amount of H3O plus and OH minus. And Kw is the amount of ion product in the water. And the Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14. This is called our equilibrium constant. And it's important, it actually applies to all aqueous solutions, acids, bases, salts, and non-electrolytes, not just to pure water. So this is our Kw for all the things that we ever do. 1.0 times 10 to the negative 14. All right, and here's a diagram that shows the self-ionization of water. What's happening is we have our water molecule here and our water molecule here. And one of the hydrogens is going to leave this water molecule and end up right here, you know, making this hydrogen on here. And that leaves a OH alone. When that moves over, it actually changes the charge of both of these so that I get the hydronium, which is a plus, and the hydroxide, that is a minus. So the Kw formula specifically is this piece right here. And what does Kw equal? It equals 10 to the negative 14th. And the question here is, how would you find H3O if you know OH minus? Well, we can take a look at this formula that we have, okay, that we just talked about. And we can solve for H3O so that it's alone. Because if we know OH minus and we always know Kw, because it's 10 to the negative 14, then we'll be able to solve for H3O plus. All right, let's go ahead and get into some formulas. You might take a second and pause and write these out, and then we'll get back to this. Okay, it's important to understand that H3O and H plus are the same thing. We talked about that earlier. So when we talk about this, H3O plus is the same as if I was saying concentration of H plus. And if we went back to our equation here, it's the same. So this could also be replaced by H plus. All right, so let's do a little bit of practice. If the concentration of H plus equals 1 times 10 to the 10th, what we're going to do is we are going to plug that into our equation. Remember that pH equals, whoops, it's right up here, negative log of H plus. All right, so pH is going to equal negative log of, if this is our H plus, we just plug that in. So here's this, so pH equals negative log of 1 times 10 to the negative 10th. Now, this is where you start getting tricky. If you plug this into your calculator and you get error, what's happening is some calculators, you can put it in like this, especially like graphing calculators or calculators where you can look back and see your work. But some of the more simple calculators like the TI, what they want you to do is write this portion first, the 1 times 10 to the negative 10th. Put that in, right? You'll put 1 exp negative 10, and then you hit it with a log. And so then you are going to push a log afterwards on certain calculators. So if you're getting a lot of error calculations, I can also help you with this in class. So plug this in and then take the negative of it. So you're going to end up with negative 10, and the opposite of negative 10 is a pH of 10. Now that's really nice and easy because it's one of these 1 times 10 to the deals, which means like you might be able to even look at this and say, well, of course the pH is 10. But down here, what if the concentration is not nice and even? 1.8 times 10 to the negative 5. We need to figure that out as well. So I say pH equals negative log of 1.8 times 10 to the negative 5, and I'm going to close the parentheses there. If I put this into my calculator, I'm going to get negative 4.74. That's a decimal. Which means that my pH is 4.74. It's always going to be somewhere around this number right here. All right, so if it says negative 5 and then you get like a number here of like, I don't know, 18, then, well, A, you know you're wrong because there's nothing that has a pH of 18. But B, it's a good double check to just kind of see that there's a relationship, that these are kind of close to each other. So here's a couple more that we want to try. Anytime that you see, remember that the brackets just mean concentration. So you can take this and it really means that I have this. And because hydrochloric acid is HCl, this actually means that I have a hydrogen concentration of 0.15. And since HNO3 is also an acid, my H plus here is going to be this 3 times 10 to the negative 7. So let's go ahead and work these out. All right, so find the pH of a 0.15 molar solution of hydrochloric acid. Go ahead and try this on your own. Pause and see if you can pick out how to solve this. All right, now that you're back, let's go ahead and work this out. So pH equals negative log of the concentration of H plus. All right, I guess we didn't need that first parenthesis, but now it's weird not to put another one. Okay, so we can say this equals the negative log of 0.15. All right, so all we have to do is plug this into our calculator, and we're using log base 10, so you don't need a fancy log with an E or anything like that. It should just be the plain old log that's on your calculator. All right, so 0.15, the log of 0.15 is negative 0.824. Now, I had a negative, so I need to bring that down as well, so we're going to have to do negative times this, and so our pH in this case equals 0.824. So let's try to find the pH of this substance right here. We know it might be somewhere around a 7, so that's a good hint. Let's go ahead and start. pH equals negative log the concentration. So we're going to put this in. So this number right here is negative 6.52, and I have to bring down this negative, and so that means that when I find the pH, it equals 6.52. Easy. We can actually go the other way with this as well. So if the pH of a soda is 3.12, then what is the hydrogen ion concentration? What we want to do is change this equation so that it is solved for H+. And in order to get rid of the log, you actually need to use the anti-log, and because this is log base 10, 10 to the power of the negative pH will be equal to the hydrogen ion concentration for any solution. So if the pH of Coke is 3.12, then all we need to do is 10 to the negative 3.12, and that will be our answer. So just plug that into your calculator. And I found a hydrogen ion concentration of 7.59 times 10 to the negative 4. And that would be our hydrogen ion concentration. So in order to find the anti-log, or the 10 to the negative, or the 10x button is what it often looks like, you want to find the shift button, and usually it's below the log button. So you'll see like the log button, and then behind or like above the log button there will be like a little 10x. Alright, so if a solution has a pH of 8.5, what is the molarity of hydrogen ions in the solution? So if we said pH equals 8.5, well, we know that 10 to the negative pH equals the concentration of hydrogen ions. So 10 to the negative 8.5 is 3.16 times 10 to the negative 9. Alright, so this is the end for now. We didn't do any calculating of the pOH, but we will go ahead and get to that in class. Hopefully you understand that pH calculations, and we'll be ready to go when you get to school. See you soon.